The final stretch here, kids, so hang in there. Today we're going to be talking about titrations and chemical equilibrium. Anytime you need to pause the video, please do so. This week I've had a fun special delivery at my place. Got this little sign from Ms. Teakle and Mr. Curtis, so really encouraging to get a little sign from them. So that'll be my picture for this week. All right, so we're going to be looking at titrations, which are a lab technique that can be used to find the number of moles of solute in a solution. The setup looks like this. You have a flask filled with an unknown liquid. Well, we know what it is, and we don't know what the concentration is. And then you have another chemical in what's called a burette, which is kind of like a very fancy graduated cylinder. It's very precise. It has this valve at the bottom called a stopcock, where if you turn this, the solution will drip out into the flask below, and you can use this information to figure out the concentration of your what's called the analyte, your unknown. Okay, an indicator is added to the unknown solution. The indicator changes color at what's called the end point, and that will tell us when the titration is over, because often our solutions are clear and colorless, and we don't know when the reaction has been completed. Hopefully, this is also when the moles of the acid and base are equal, which is called the equivalence point, and typically we're doing an acid-base reaction here with titrations. So again, in the flask, let's say we have an acid. Let's say in the burette we put a base. We add the base until the moles of the base and the acid are equal. So let's say you had to add 1 mole of hydroxide ions. That means you had 1 mole of acid ions, of hydrogen ions. And when that happens, when those are equal, the indicator changes color. So in this example down here, we had sort of a pink color that is called phenolphthalein. It's really bright pink, which is fun. Okay, so I'd like you to pause this video and watch at least one of these other videos that shows the process of doing a titration. Unfortunately, you won't get a chance to do this in the lab, but if you come back and do more chemistry, like in AP Chemistry, then you can see what those are like. All right, now during a titration, let's say we have an acid in the flask and we're adding base to it, the pH will change during that titration. So if we take a look at this graph, we have the pH on the y-axis. We have the milliliters of base that we're adding on the x-axis. So at 0, we've added nothing. Okay, so we can see at the beginning of the titration, we have a low pH of about 3 here. Below 7 is an acid, above 7 is a base. So as we add more base, we can see that the pH is increasing. It doesn't increase in a straight line, though. We have this interesting shaped curve. Okay, so after you add a little bit of the base, the pH goes up, and it reaches this point right in the center where the pH rises very rapidly. And that is because all of the acid, the hydrogen ions, are being neutralized by the OH ions. So the pH rises very rapidly at this point. So in a titration, you want to stop when the indicator changes color, and that's going to happen very close to what's called the equivalence point. It's a pH of 7. If you have a strong acid, strong base, it's going to be a pH of 7, and then that point is called the equivalence point. Okay, if we were to add more base, which in a titration with an indicator, we wouldn't add more base. We would stop right here. Once that solution changes color to pink, then we're done. But if we were to add more base, you can see that, of course, the pH continues to rise. It flattens out eventually because, you know, if we're adding more base, it's not going to become even more basic forever. It's going to stop at some point, depending on our concentration of base. Okay, so please pause the video and answer these questions. Give those a think. Here are the answers. As usual, I'm posting the slides on Schoology also. If you have any questions about any of these, please come see me in the Zoom meeting. All right, so let's do a sample problem on a titration. A student uses a standard solution of 0.291 molar potassium hydroxide to titrate 49.46 milliliters of hydrochloric acid, which is HCl. She finds that it requires 42.55 milliliters of the base to reach the end point of the titration. What is the molarity of the acid solution? So there's a lot of words here. I would suggest underlining and labeling some things. So these two values are for the base. This value is for the acid. You may also want to label this like so. Okay, now step one of solving a titration question, and we know it's a titration question because we have acid and base here, but we want to balance the chemical equation. Okay, so we have our two chemicals here, KOH and HCl. So please pause the video and balance these. I'll remind you that the OH goes with the H and the K goes with the Cl. All right, here they are. Okay, so step two is to convert the given to moles. Now we're going to start with the base here because we have two numbers that go with the base. We know the molarity is equal to moles over liters. So take a moment and solve for the moles of base. Okay, here's the answer. Now, if you want, you can do a little shortcut, which is to leave the volume in milliliters instead of changing to liters. If you do that, you'll end up with millimoles instead of moles, but it'll work out in the end, so don't panic that it says millimoles there. Step three is to convert to moles of acid. You're going to use your balanced equation and just a little bit of stoichiometry to do this. Okay, so we can see that it's a 1-to-1 ratio with our HCl and our KOH, so it's an equal number of moles of base and moles of acid, so that's easy. Step four is to convert back to our required units. So all of these are very similar to our stoichiometry steps that we did earlier in the year. Okay, so take a moment and solve for the molarity of the acid. All right, here it is. Now, if you did not change the volume earlier for the base, you don't change it the second time either, but you can see that you get the same answer. It's a little bit of a shortcut. Now, there's even a better shortcut because it's a 1-to-1 ratio. MA times VA equals MB times VB. When we multiply the molarity and the volume, we get moles. In other words, right, molarity is moles over volume. If we multiply the molarity times the volume, you can see that the volumes cancel out and we're left with moles. So in other words, this equation is showing moles of acid is equal to moles of base. Now this is only going to work if the acid and base are in a 1-to-1 ratio in your balanced equation. So no coefficients in the balanced equation. So I'd like you to try that same problem again, but using the shortcut this time. All right, so here it is. You can see that we got the same answer. Okay, so again, I want to pause the video and do problems 1, 2, 3, and 4. I gave you some hints in the notes. Some of them you can use a shortcut, some of them you can't. So give it a try. If you need help, please come see me in the Zoom meeting. As long as you turn the homework in, by Friday, but I want to see something in by Wednesday, then you should be fine. There should be enough time for you to finish this work. All right, now one last topic here of chemical equilibria. This is almost the final topic of the year, by the way. So I'd like you to think about a closed bottle of water. Okay, and if you don't know what that looks like, I found a really crappy stock photo of it. Okay, some of the liquid water is evaporating into water vapor, and some of that water vapor turns back into liquid water. Both of those things happen at the same time, so liquid to gas, gas to liquid. And if the temperature is staying the same, both of those happen at the same time at the same rate, and that is called equilibrium. That's one example of equilibrium. Okay, so give this a think. What would happen if you raise the temperature by 5 Celsius, and what will happen if you open the lid of the bottle? So give that a think. Pause the video. All right, so if you raise the temperature, we would expect that more water would evaporate into water vapor. Okay, and if you open the lid of the bottle, eventually the water vapor will leave the bottle and you'll have no water left in the bottle. And I want to point out that the bottle is not empty because there is air. You may have seen this before, but little joke there. Okay, now this is important, an important state of things. Okay, chemical equilibrium is the state of a system in which the rate of the forward reaction is equal to the rate of the reverse reaction. It does not mean that you have an equal amount of water vapor and gas in the system. Okay, you're going to have a lot less water vapor probably, depending on how much liquid water's in there. But in our equation, or in our example, we have our forward reaction is liquid turning to gas. The reverse is gas to liquid. And the way that we show this in equilibrium is with a double-sided half arrows. So that is the equilibrium symbol right there. Okay, now Le Chatelier's principle is this idea that when you put a stress on the system will respond to relieve that stress. So as we discussed earlier with increasing the temperature, that pushed the reaction toward the gas side. If we change the concentration, we can also change the pressure. That will change how much of each chemical we have in the system. So that's called Le Chatelier's principle. We're going to come back to that more next week. Okay, now another example of an equilibrium system is ocean acidification. So carbon dioxide, we know, can dissolve in water. That's why we like drinking sodas. The carbon dioxide's bubbly. It feels fresh in your mouth, right? That does create carbonic acid. So that's one of the reasons that soda is so bad for your teeth, is because it lowers the pH of what you're drinking. And can damage your teeth. But at any rate, so we have carbon dioxide and water that makes carbonic acid. That carbonic acid goes on to dissociate or to split up into two separate pieces. We can see the hydrogen ion there, of course, is the acid piece of this. It is a weak acid, but over time it does have a big effect on the oceans. So you may recall please recall the Keeling curve here. So starting in 1958, the CO2 levels have steadily increased. And as a result of the steady increase of CO2, we can also see there has been a decrease in the pH of seawater. So that data goes back to the mid-80s. The blue line there, Aloha seawater pH. Right? So we can see that the pH is decreasing over time because of the increase in CO2. So we added CO2, we added an increase of CO2, which caused a decrease in the pH. Now we'll notice that the pH is actually basic, so the pH is above 7, but because the pH is decreasing, we still call that acidification. Okay, so again, give these a think about how the pH changes. So pause the video, give those a think. Here are the answers. And finally, the answer to the puzzler. Parallel universes. Okay, good luck this week, and please come see me in the Zoom meeting if you have any questions.